Okay. Uh, so let's first go through the that number 4 that I was sort of struggling through at the end of class last time. I want to point out this isn't what makes this problem hard isn't really thermodynamics, it's math. But let's just go through the math, think through it carefully. So we have 1 kilogram of refrigerant. It gives us a pressure and a specific internal energy at the first instant and the second instant. It says this problem is in the differential first law stuff. We're going to use the standard first law, but in order to do that, we need to understand the relationships between the differential things and the difference things. In calculus, did you guys talk about differential and difference stuff? You know, like the difference stuff is when you had the change in operator, or you had just a finite value minus a finite value, and the differential stuff is once you go into the calculus, the limits and stuff. The
Some of my professors just called it delta, whatever.
Yeah, delta, right. But that's so when I say like the difference formula, it's that delta formula. That's the standard form of the first law is the difference formula. That's all I'm trying to. And okay, so let's just write down what we know, and then we'll think about the math a little bit. So instant 1, we know that the pressure is 0.9 times 10 to the 6 pascals. And once you multiply the specific internal energy by the mass, you get a true internal energy of 232.92 times 10 to the third, and this is in joules. And then at instant 2, we have P2 is equal to 1.2 times 10 to the 6 pascals. So the pressure goes up a little bit, and the true internal energy is 276.67 times 10 to the third joules. And then it says the paddle wheel does some work. And okay, so here's where this, it takes a little thinking to put the pieces together. This is real thermodynamics. This isn't just math. It's saying, the paddle wheel transfers energy at a constant rate. And so, in other words, W dot is plus or minus, this constant rate is 0.1. It's in kilowatts, so this is 0.1 times 10 to the third watts. Just like I do in statics, for the people in statics, I'm always going to put a little hat on my capital W when it's talking about work, and I'll leave it plain when I'm talking about watts. So hopefully that'll help clarify things a little. This stuff can get a little confusing. And then we have to think about the sign. So the paddle wheel is doing work onto the system. The refrigerant is our system. So that means we want the negative here. And then the mathematical stuff comes in with the rate of work. So it said, with the rate of heat. Heat transfer occurs from the refrigerant at a rate of kT, and this is in kilowatts. But T is in minutes. Okay, so this is going to take a little thinking. So we have plus or minus. KT, and if I want to put this in, watts, I guess I would write this as K times 10 to the third T, and now that's in SI units. Okay, but T is in minutes. Okay, so I'm gonna write this out with two different time scales. This is us. But our uh, time scale T is going to be in minutes. And I'm going to use a time scale tau to be in seconds. Okay. And the relationship between those is the one in seconds is 60 times the one in minutes. And now I'm going to write out, well, so we're heading towards this. We're going to use the change in internal energy is equal to Q minus W. But in order to do that, we have to figure out how to go from this these rate value things that were given and put them into this form. So notice that so Q dot, you can think of that as dq d, and which time scale do we want? Okay, this is tau, right? Right. So everything that's in SI units is going to be using tau. Okay. And this is equal to, this is leaving the system. I didn't do the sign, but so that's going to be negative. So dq d tau is equal to negative k times 10 to the third t, and that t is a different time scale. We'll deal with that later on. But now we can, now that we have this written in this differential form, I can integrate this. So I'm going to multiply both sides by d tau and get dq, ooh, dq, that sounds good on a hot day, is equal to negative k times 10 to the third t d tau. So now we have this hideous thing with two different time scales in it. Okay, but now we can integrate both sides. And if you integrate d tau, dq, normally if you integrate something, you get a change in that thing. Since q is already a change, this just gives you q back. You know, like delta q doesn't really have a meaning. Q is already a change. And so this is equal to the integral from time 0 to time 2. I'll write this as tau 2 of negative k times 10 to the third t d tau. That tau 2, so this is happening over 20 minutes, and 20 minutes is 1200 seconds. So that tau 2 is 1200. So we got 0 to 1200, negative k times 10 to the third t d tau. So now we're almost ready to do that integration, except we can't integrate this t with respect to tau. So first we have to use the relationship between those to substitute in. And we have the relationship right somewhere. Tau is equal to 60t. And so what's t equal to? Tau over 60. And so I'll plug this in and we get the integral. I'll pull the, well, integral from 0 to 1200. T we're replacing with tau over 60. So this whole constant is negative k times 10 to the 3 over 60. And then tau d tau. And now we have something we can integrate. So this q is equal to, I'll pull this stuff all outside, negative k times 10 to the third over 60 times the integral of tau d tau. That is tau squared over 2. We're evaluating from 0 to 1200. So that's right. So that's 120. So we can write this as negative k times 8.3 repeating. That's 1,000 divided by 60. Sorry, that's 1,000 divided by 120 because I'm also including that 2 in there. And then we're multiplying by 1,200 squared. So 1.44 times 10 to the 6. And so you get negative 1.2 times 10 to the 7 times k. All right, so that's our Q. Our W is easier, but it's the same idea. Really, all of this integral stuff, you don't have to worry about this to get ready for tests. I'm not trying to make this like a calculus class. But what you should try to understand from this problem is the relationship between the Q dot and the Q, and the relationship between the W dot and the W. So this work one is more the kind of thing that you should expect to, be able to do. So we have that work dot. I'm going to keep using tau for this. This is equal to dw d tau, and it's equal to negative 0.1 times 10 to the third. And so dw is equal to negative 0.1 times 10 to the third d tau. I'm going to integrate both sides. Integrating dw gives w, and this is the integral from 0 to tau at that second instant, which is 1200 again. Negative 0.1 times 10 to the third. You can pull the constant out, so this just ends up being negative 1200 times 0.1 is 120, so negative 120 times 10 to the third. And now we have the difference in the internal energies. So that's 276.67 minus 232.92. So our change in U, so this is going into the first law now. We're putting it into this form. The delta U is 43.75 times 10 to the third is equal to negative 1.2 times 10 to the 7 times K. And then minus negative 120 times 10 to the third. And so we get 1.2 times 10 to the 7 K is equal to 76.25 times 10 to the third. And so K is 6.35 times 10 to the minus third. Okay. So the tricky thermodynamics thing was understanding the integral relationships between Q and W and Q dot and W dot. And then the tricky math thing, whatever, like little by little, you're just supposed to be absorbing this stuff as you go through these classes, but that's not a key point really. Yep.
So if this is a different answer than the one like we got,
Yeah.
we resubmit this one?
If you have time to redo it, redo it. I mean, it won't change your points or anything for
Okay.
the class, but
And so just to be sure, we got delta U in that first law from taking the difference of U2 and U1.
correct. Yes, exactly. Yep. Okay, so there's that. Let's never talk about it again. So now exam 1 is on Friday, a week from Friday. So that is the 26th, I think. And for that, let's just do topics up through the differential form of the first law. So all the stuff we'll do from now until then is not going to be on the test. So no simple compressible substances. That's the next thing we're going to get into. Okay, so now we're going to get into simple compressible substances. Um, and every material that we're going to discuss in this class is in this category. So every material in this class is a simple compressible substance. Um,
Are there some typical day-to-day examples of a substance like that?
of a simple compressible substance, yeah, I mean water, uh, gasoline.
Could anything be considered that? Because it seems a little open-ended, just like simple compressible, like
Yeah,
there are
so
some that are very extreme and some
um,
that are less
it,
so.
we're going to be considering substances that are homogeneous. So here are the requirements. Homogeneous means that wherever you go inside the material, it's the same. So, like a sugar cookie is homogeneous, but a chocolate chip cookie is non-homogeneous. Okay. Um, the people in D form, I gave the example of homogenized milk, but I'll spare you all that one this time. um, so homogeneous means there's no chunks of anything, no lumps. Um, and uh, then the second requirement is just that it's unaffected by magnetic or electric fields. So like we'll talk mostly we'll do calculations with water in its different phases, but we'll talk about some high tech refrigerants and that kind of things. But all of these things that we talk about, including uh, most all of the stuff that we get off the periodic table, nitrogen, oxygen, helium, are all simple compressible substances. Um, Talking about the first law, we've been talking about an equation that deals with processes. So the first law deals with processes. Um, that's going from one state to another. Um, in talking about simple compressible substances, uh, so we'll largely here in simple compressible substances be talking about equations of state. And an equation of state is one where we know some properties at a state. What can we say about other properties at that state? At that same state. So those are equations of state. It's worth remembering that term. Um, and remember, I mentioned this once before. When a material is not undergoing a phase change, any two properties define the entire state. So for example, if you have water that's not at a phase change pressure and temperature, and you're told what the pressure is and you're told what the temperature is, um, there is only one entropy, one enthalpy, any other property, one specific internal energy, any other property you can think of, there's only one of those that's possible at that point. Okay. That doesn't mean that we know it, you know, and this equation of state stuff is largely just figuring out ways to take those properties that we're given and get the other stuff. It doesn't mean that we know it. It just means that it can't be anything else. Okay. Uh, what about if it is undergoing? So when a material is undergoing a phase change, any one property defines the entire state. Uh, and when it is undergoing a phase change, this is called saturation. Nope. I guess you could think of it as like, why is it called saturation, undergoing a phase change? I guess you could think of it as like when liquid water gets up to its boiling temperature, um, it is about to change to steam if you add any more internal energy. So you could think of at that temperature, that water is saturated with internal energy. The same way like when the air gets to maximum humidity, it's saturated with water. Any more moisture in the air comes down as condensation. This is saturated with internal energy. Okay. Uh, so these are important. These are going to come up in quizzes. So now, what can we say about simple compressible substances? The pressure, specific volume, and temperature. So this is the specific volume, the volume per mass. Of a simple compressible substance can be shown on what's called a PVT surface.
Professor?
Yep.
What does T stand for again?
Temperature. Um, there are two slightly different like qualitatively fundamentally different PVT surfaces for materials. Different. Qualitatively, fundamentally different. I mean, they're all different, like numerically, they have slightly different heights and stuff, but they all have this same shape I'm going to show you. Um, PVT surfaces. So the first one is materials that contract upon freezing. Contract when they freeze. So let me show you what this looks like.
So there are other materials other than ice that also expand?
Not that I can think of. Maybe there's some. Maybe you can make them in a lab or something. But right. Yep, that's right. Let's see. So, whoops. Where's my desktop? So, PVT surface. Blow this up a touch. Okay. So here is what it looks like. And, it's pretty complicated to make sense out of, but you can see that the three axes are pressure, specific volume, and temperature. And this represents one single material, but all materials that contract when they freeze have like a similar shape. And you can see the little, this little ridge here shows that it contracts when it freezes. So at a constant temperature, when you get to this dividing line between solid and solid and liquid, that phase change right here connecting them, the volume of the material drops down. Okay, so when we see the one for water, that ridge is going to go the other way. So I'll put that up here too. But so that's you can look at this and say like, okay, at that phase change boundary, the volume goes down. And so this is not water, it's some other material.
Professor?
Yes.
So in that one, the volume and the pressure are like separate?
The volume and the pressure, yeah, they're all separate. Yeah, they're all independent of each other.
If there's a low pressure and a low temperature, increasing the volume will make it turn from solid and vapor to solid?
Yeah. Right.
Like just having more of it will cause that, or?
Well, that's a specific volume, so it's volume per kilogram. So you can't. It's not about just putting more in. It's like the reciprocal of density. Yeah. What?
Can I ask a question?
Yeah.
Is like the thing shaped that way just because like some combinations of pressure, specific volume, and temperature just like not possible, or like?
Well, it's not finite like that.
Yeah.
So it goes on forever in all these directions. But that's definitely true. Well, there is something weird happening here, and we'll talk about that, where when you get a temperature and a pressure that's higher than this point here, liquid and gas lose their distinction.
Okay.
There starts to be just one thing that's not a liquid or a gas.
Is
But-
it something that kind of exhibits the properties of several, I guess, it's a matter, or?
Well, it has sort of properties of both, and it moves like a fluid, and you don't want to touch it. It's very hot. But what's important to us as engineers, and I mean important to scientists because it's more interesting, is what happens around the phase change boundary. So that's why we're looking at this part of it, and maybe there's some creature that only cares about the part that's a mile this way or whatever, but this is the part that we care about, what happens when the phases change.
Like other graphical representations for material, maybe like 3D modeling online that you know of, just so we can better see it rather than like a.
Yeah, I mean, you can Google it. I'm sure there are probably three-dimensional things. I've thought about doing a 3D print of one, but what we're going to see is that for different types of calculations, we'll look at different two-dimensional projections of this. It's pretty hard to get a sense of anything 3D on a page. But so this is what it looks like for water. And any other material that expands when it freezes.
Question.
Mm-hmm.
So like when we're talking about that like surface, if we're below it, it's like the solid and vapor. Then above it, it's a gas. For that one at least. Or
Let's just not think about it this way too much. I'm just showing you that there is such a surface.
okay.
And if you know two of these things, it fixes what the other one has to be. That's a property of a surface. But what's really going to be useful to us is two-dimensional projections. But you can see here, if you just glance at this phase change boundary, as you go from liquid to solid, you can see that the specific volume of the material increases. So that's what happens with water, which is lucky for anything that lives in water because the fact that, so when water freezes, it turns into ice, which becomes less dense and goes to the surface. And so the warmer water stays below and the ice rises above. If it was the other way around, the colder water would drop down as it freezes, and the entire, the cold from above would eventually just freeze the entire body of water. But what happens in a lake instead is that the coldest water gets to the top, creates this barrier, and then things can live in the water during the winter.
Also, the insulator from the water to an extent, as well
Mhm.
as that's on top. And all of that.
Yep. Okay, so we will normally just look at projections. Um, use two-dimensional projections of this surface. So let me pull something up here. Okay, so you can see in the top corner there is like a PVT surface, and you can see how like um, if you fix the third variable, fix one of those variables, you can make projections off in the different directions that show you relationships with two of those variables. And so we're going to do things like this. Um, the most important feature and the thing that's going to be kind of that we're going to want to keep focused on as we use these um, of the PVT surface is that arch in the middle, the liquid and vapor section, and it is called the vapor dome, and you'll see it in just about every projection. And it always looks, it can be sort of warped to the side or whatever, but it always looks something like this. Um, and over here, in red represents a saturated liquid. Um, to the left of it is a liquid. Inside the dome is a mix of liquid and vapor. On this side of the vapor dome is a saturated vapor. And then over on this side is a vapor. And then there's two other features here. This is called the critical point, and I'll talk about that in a second. And this is called the triple line. Okay, so a couple things to keep in mind about this. So one is this represents a single phase change region between liquid and vapor. So why do we in this class care about the change between liquid and vapor, and we don't care as much about the change between solid and liquid? Yeah, but there's a reason that we are, and that is that there is a huge amount of energy between the liquid and the vapor state, and there's a lot less energy between the solid and the liquid state. So for us as engineers who are always trying to extract energy from things, this is the one that's useful to us. Okay. So that's important in engineering because it represents a large amount of energy. a lot of energy. Second, the triple line is the region where all three states can exist in equilibrium. So solid, liquid, and vapor exist in equilibrium. And third, the critical point is the pressure and temperature above which there's no distinction between liquid and vapor. And when you get above the critical point, that state is called a supercritical fluid. Okay, so I'm a little over right now. We'll start here next time.